भी आ सकते हैं।
सर आप किन डेज में
ट्यूसडे से लेके सैटरडे तक।
जी सर सर पेज नंबर निकालिएगा एक मरतबा।
सर बस यहीं पे
वेट।
जी सर सर ये यहाँ पे कंप्लीट हो जाता है।
एक मिनट। जी, ये नोट कर लिया आपने?
जी सर कर लिए।
ओके।
सर कर लिया नोट। सर 2.3 भी थ्योरम आपने करवाया?
इससे प्रीवियस थ्योरम भी आप नोट करना?
यस सर, वो भी करना नोट।
ओके। ये नोट कर लिया?
जी सर ये किया हुआ है सर 2.3 थ्योरम।
सर इसके लास्ट से करना।
सर इसका नेक्स्ट पार्ट
2.1 के लास्ट।
ओके।
ओके सर, हो गया, थैंक
सर 2.3 भी
ओके।
प्लीज।
नेक्स्ट टर्म जो है वो 2.4 है।
सर 2.3 2.4 है नेक्स्ट 2.2 से।
हाँ।
जी सर वही निकाल।
Well, see another theorem. This is suppose F is to find our AB cross R to R is continuous and satisfy the uniform Lipschitz condition with respect to F on AB cross R with Lipschitz constant K, that is F of T S minus T by absolute is less equal to K into F minus Y absolute for all T X T Y belong to AB cross R. For F is continuous and is Lipschitz, if B minus K is less than pi over K square root, then this boundary value problem, this is d to f by dt square is f of t x t belong to AB. Also x at is A, x at B is B. Then this boundary value problem has a unique solution. Well, see proof of this theorem. This is consider x a Banach space of continuous functions over AB with norm defined as x norm is maximum of x of t absolute over rho of t and t varies from A to B, where rho is a positive constant continuous function defined on AB such that there is some constant alpha less than 1 satisfying k into 1 over rho of t integral from A to B g of t as rho s ds is less or equal to alpha for t belong to AB. So rho is a solution of this inequality. So you can see X is a solution of boundary value problem. This boundary value problem, if and only if X is a solution of this integral equation. So you can see this can be expressed as this. So X is a solution of this boundary value problem. If X is a solution of this integral equation, this is X of t is b minus a into t plus ab minus ba over b minus a plus integral from A to B, g of t as f of s x per ds, where g of t as is a Green's constant defined as g of t as is minus 1 over b minus a into t minus a into b minus s, where a is less equal to t is less equal to s is less equal to b. Also, g of t as is minus 1 over b minus a into s minus a into b minus t, for a is less or equal to s is less or equal to t is less or equal to b. So x is a solution of this boundary value problem if and only if x is a solution of this integral equation. But define a map t from x to x by t of x is b minus a into t plus ab minus ba over b minus a plus integral from a to b g of t as f of x x over ds. So the given boundary value problem has a unique solution if and only if the map T has a unique fixed point. So fixed point of T is a solution of the integral equation. So you can say boundary value problem has a solution. Now for x5 belong to x, consider tx minus ty absolute over rho of t is less or equal to 1 over rho t integral from A to B g of t as absolute f of x x of s minus f of x y s absolute ds. Now you can see f satisfy a uniform Mises condition. So you can see this is less or equal to k into x over x minus 5 as absolute. So this is less or equal to 1 over rho t integral from A to B g of t as absolute into k into x over x minus y as absolute ds. Now just multiply this by rho s also divide this by rho s, so you can see this can be expressed as 1 over rho t integral from A to B g of t as absolute into k into rho s into x of s minus y of s absolute over rho s ds. Now this is, you can see this is just less or equal to x minus y norm. So this is k over rho of t integral from A to B g of t as absolute rho s dx x minus y norm. Now this is so you can see T is a contraction mapping because you can see this is less or equal to alpha and alpha less than 1. So you can see T is a contraction mapping. And by contraction mapping theorem, T has a unique solution. Also, you can see rho of T can be chosen in this way. Rho of T is sine of K over alpha square root into T minus T, which is some constant less than A. So rho of T is a solution of this differential equation d2 rho over d square plus K over alpha rho is 0. Also, rho of T is greater than rho of T is rho of B into T minus A plus rho of A into B minus T over B minus A plus and derived from A to B d of Ts into minus K over alpha rho s ds. So this is greater than equal to, you can see this is greater than 0, so this is greater than equal to derived from A to B d of Ts into minus K over alpha rho s ds. So this is so rho of T is greater than equal to A to B d of Ts absolute K over alpha rho s ds. So you can see rho so you can see rho solution of this inequality as this has a solution. So overall you can see T is a contraction mapping, and so T has a unique point. So this integral equation has a unique solution. So you can say a given boundary value problem also has a unique solution. This also has a unique solution. नोट करिए
सर स्टार्टिंग से एक दफा दिखाइएगा, ये थोड़ा सा रहता है। जी सर, नेक्स्ट पेज।
नोट कर लिए?
जी सर हो गया, स्क्रीनशॉट कर लो।
Well, see another theorem. This is assume that x is a function defined over AB cross R square to R is continuous and satisfies the uniform exchange condition with respect to x and x dash, and f of t x u minus f of t y v absolute is less equal to k into x minus y absolute plus L into u minus v absolute. For t x u t y v belong to AB cross R square. For F satisfies uniform exchange condition, this where L is greater than or equal to 0, also K is positive. If K into B minus A square over 8 plus L into B minus A over 2 is less than 1, then this second order multivariate problem, this is d to f over dt square is f of t x f dash, and t belong to AB, x at is A, x at B is B, has a unique solution. Well, see proof of this theorem, this is consider F a Banach space of continuously differentiable functions on AB where non x norm is maximum of k into x of t absolute plus L into x dash of t absolute and t varies from A to B. So this is a non defined in this space. For x is a solution of the given boundary value problem if and only if x is a solution of this integral equation. This is x of t is b minus a into t plus ab minus ba over b minus a plus integral from a to b d of t as f of x, x of x, x dash of x ds, where g is Green's function g of t as is minus 1 over b minus a into t minus a into b minus s, for a less or equal to t less or equal to s, t less or equal to b. Also g of t as is minus 1 over b minus a into s minus a into b minus t, and for a less or equal to s, t less or equal to t less or equal to b. Define a map t from x to f by t. X of t is b into t plus ab minus ba over b minus a plus integral a to b d of t as f of x, x to x, x dash to s ds, for T belong to AB. Then the given boundary value problem has a unique question if and only if the map T has a unique fixed point. So for F5 belong to S, consider K into Tx minus Ty absolute, where F5 belong to S, so just consider K into Tx minus Ty absolute is less or equal to K into integral from A to B G of Ts F square X square S dash square minus F square 5 S y dash square Ds. This is less or equal to K into integral from A to B G of Ts absolute. This is less or equal to K into F square minus 5S absolute plus L into F dash square plus minus y dash square absolute. This is because you can see F satisfy uniform basis condition. That's what this is. Now you can see this is less or equal to F15 norm. So this is less or equal to K into integral from A to B G of Ts the absolute Ds into F minus y norm. Now you can see integral from A to B G of Ts absolute Ds is less or equal to B minus A square over 8. So K into Tf minus Ty absolute is less or equal to K into B minus A square over 8 into F minus Y norm. Also, consider L into T x dash of T minus Ty dash of T is less or equal to integral from A to B partial G over partial T of Ts absolute to F of x x of x minus f dash of x minus F of x y of x y dash of x ds. Now you can see F satisfies uniform condition, so this is less or equal to K into F of x minus y of x absolute plus L into f dash square minus y dash square absolute ds. So this is less or equal to L into integral from A to B partial G over partial T of Ts into K of K into F square minus y dash absolute minus L into f dash square minus y dash square absolute ds. Now this is less or equal to F minus y norm, so this is less or equal to L into integral from A to B partial G over partial T absolute ds into F minus y norm. So this is less or equal to L into B minus A over 2 into F minus y norm. You can see this partial derivative G with respect to T absolute integral is less or equal to B minus A over 2. Now from these two inequalities you can see Tx minus Ty norm is less or equal to alpha F minus y norm, where alpha is K into B minus A square over 8 plus L into B minus A over 2, and this is less than 1. So you can see T is a contraction mapping. So T is a contraction mapping. So T has a unique fixed point. So T has a unique fixed point. The integral equation also has a